Welcome back, Deep Divers. You guys sent in a ton of articles this time around, and looks like you're really interested in broadcast technology.
Yeah, it looks like everyone wants to know how digital media goes from like the camera all the way to you hitting play on your screen.
And there are so many acronyms, it's a bit intimidating.
Absolutely, it can be a real alphabet soup.
But that's why we're here. We'll break it all down, decode those acronyms, and get to the core of how it all works.
Ready to dive in?
Absolutely. So the first thing that jumped out at me was all those protocols, TCP, UDP, IGMP. Can you give us a quick rundown of what these protocols are and why they matter in broadcast tech?
You got it. So think of protocols like the rules of the road for data traveling over the internet. They make sure everything gets where it needs to go smoothly and efficiently. Let's start with TCP. TCP is all about reliability, like making sure a package arrives in perfect condition no matter what.
Okay, so it's the careful one. I get it.
Exactly. And that's why it's used for things like downloading files where you need every single bit of data to be accurate.
Makes sense. But what about when speed is everything? Like with live video?
You're right on. For real-time stuff like live streaming or video calls, we rely on UDP. It prioritizes speed over everything else. It's like a live messenger racing to deliver a message. Even if a few words get jumbled, the message still gets through quickly.
So TCP is the careful one, and UDP is the speedy one. Got it. But what about IGMP, multicast? Where does that fit in?
Multicast is all about efficiency. It's like a radio broadcast, one stream, multiple listeners. Imagine a webinar, for example. Instead of sending separate streams to each viewer, multicast allows you to send one stream that everyone can tune into.
So it's about efficiency. Instead of clogging up the network with a bunch of streams, multicast sends one, and everyone can tap in.
Exactly. IGMP is the protocol that manages who's listening and makes sure the stream gets to the right people. It's crucial for things like IPTV, where lots of people watch the same channels at the same time.
It's like a traffic cop for the streams.
Pretty much. Now, you mentioned how much video delivery has evolved. We've gone from those grainy videos to streaming 4K movies on our phones.
It's mind-blowing how quickly it's happened. But high-quality video needs a lot of data, right? How do they get all that information through the internet without it taking forever to load?
That's where video compression comes in. Think of it as packing a suitcase. You want to fit in as much as you can without making it too bulky.
I see. So it's about finding that sweet spot.
Exactly. And this is where codecs come in. They're like translators converting between the language of video and the language of the internet. They allow us to fit huge amounts of visual data into a stream that can travel the world.
The articles mentioned a whole bunch of codecs, H.264, H.265, AV1, even AVS plus it's overwhelming.
It can be, yeah. But the most important thing to remember is that codecs balance video quality with file size. Older codecs, like H.264, are good at compressing video, but they might not be the most efficient for really high-resolution content.
So what's the solution?
Newer codecs like H.265, which is also called HEVC, they provide even better compression, meaning you can get the same quality but with smaller files.
So it's a win-win.
Exactly. Smaller files mean faster downloads, less buffering, and smoother playback, especially for 4K and beyond.
So H.265 is like an upgrade. But where do the other codecs like AV1 and AVS Plus fit in?
It's a competitive field. AV1 is an open sort of codec, and it's becoming super popular.
Why is that?
Because it's really efficient, especially for 4K and higher resolutions. Then you have AVS Plus I, which was developed in China and is looking to become a major player, especially with the rise of UHD. It's interesting to see how these different codecs are all competing for the top spot.
It's like a race to see who can pack the most quality into the smallest space.
You got it. Now, I know we threw a lot of acronyms at you, but for most viewers, you don't really need to get bogged down in those details.
So we don't need to be codec experts.
No, not at all. Most streaming services will choose the best codec for the content and your internet connection automatically. The key takeaway is that this technology is always evolving, which means you, the viewer, will always get a better viewing experience.
Smoother streaming, better quality, less buffering, that all sounds good to me.
Exactly. Now, I did want to touch on the terms lossless and lossy compression. Those terms come up a lot when we talk about codecs.
Yeah, I've heard those terms, but honestly, I'm not really sure what they mean. Can you break it down for us?
Sure. Imagine you're taking a picture with your phone. Lossless compression would be like saving that photo in a format that keeps every single detail.
Okay, so it's like a perfect copy.
Exactly. It's the best option when quality is super important, like for professional photography or when you want to archive important images. Lossy compression, on the other hand, is more like saving that photo in a smaller file format.
So some details might get lost.
Yes, but the idea is to do it so cleverly that it's barely noticeable to the human eye. This is the magic of lossy codecs like H.264 and H.265.
So they kind of trick our eyes into thinking we're seeing all the details.
That's a great way to put it. They analyze the video and figure out which data you're not likely to notice, and then they just get rid of it. This results in a much smaller file size without sacrificing a ton of quality.
It's amazing how they do that. It sounds like we've gone from the basic rules of data to the magic of squeezing video into these tiny packages.
We've definitely covered a lot of ground, that's for sure.
I think it's time to give our listeners a break to process all this.
Agreed. We'll be back to delve deeper into the world of streaming, latency, and all the other cool technologies that make digital media work. Welcome back to our deep dive into broadcast tech.
I'm excited to keep going. Last time we talked about all those essential protocols and the evolution of video delivery. It's really amazing how far we've come.
It really is. And now I think we're ready to jump into the world of streaming. It's where all those technologies we talked about last time come together.
Okay, so streaming. One thing that always confuses me is, well, all those different streaming protocols, the articles mention HLS and Dash, and I'm never really sure what the difference is.
Yeah, it can seem a little complicated, but both HLS and Dash, they're what we call adaptive streaming protocols.
Adaptive streaming.
Yeah, think of them like intelligent traffic controllers for your video stream.
Okay, I like that analogy.
They constantly monitor your internet connection and adjust the quality of the stream on the fly. So let's say you're watching a movie and your internet connection suddenly dips. Instead of that annoying buffering, adaptive streaming will seamlessly switch you to a low-quality version.
So I can keep watching without interruption.
Exactly. And when your connection improves, it bumps you back up to a higher quality version. You get the best possible quality without any hiccups.
So it's like having a little video assistant making sure things run smoothly.
Exactly. And that brings us to the two different protocols, HLS and Dash. They both do essentially the same thing, adapt the stream to your connection, but they have a few key differences.
Okay, so lay it on me. What are the differences?
Well, HLS stands for HTTP live streaming, and it's Apple's preferred protocol. It's the standard for Apple devices like iPhones, iPads, and Apple TV.
Got it. Apple likes to keep things in-house.
Exactly. DA, on the other hand, stands for Dynamic Adaptive Streaming over HTTP. It's an open standard.
So it's more widely used.
You got it. It works across a much broader range of devices and platforms. So in a way, you could compare it to the iOS versus Android situation, but for streaming.
I see. So it's kind of like two different teams working on the same problem.
It's a good way to think about it.
Yeah.
But regardless of which protocol is being used, adaptive streaming has really revolutionized how we watch video online.
I agree. It's so much better than those days of constant buffering and waiting for videos to load.
Absolutely. It's become even more important as internet speeds have become more variable, what with all the mobile devices and wireless networks we use now.
And speaking of speed, there's another big thing in the streaming world, low latency.
Oh yeah, low latency is a huge deal, especially for things like live streaming and gaming.
I've heard the term, but I'm not always sure I totally get it. Can you explain?
Sure. Latency is basically the delay between what's happening live and when you see it on your screen.
Okay, so like a lag.
Exactly. High latency can be really annoying, especially if you're watching a live event. Imagine watching a live concert and your stream is delayed by several seconds.
Yeah, you'd be totally out of sync with everyone else.
Exactly. It would ruin the whole experience. And in gaming, high latency can make all the difference.
So how do we solve this?
Well, that's where LL-HLS and LL-H come in. They're low latency versions of those protocols designed to minimize that delay. They work by using shorter video segments and basically just getting the stream to you as fast as possible.
So it's all about speed, speed, speed.
Yeah, pretty much. It's essential for things like sports or esports where every second matters.
I can see that. And for gaming, being able to react quickly is everything.
Absolutely. But there's another technology that's really exciting in this area, HESP.
ESP, that one rings a bell.
It's really pushing the boundaries of low latency streaming. The goal is to achieve what we call sub-second latency, which is almost real time.
So like I'm practically in the same room.
Pretty close. Imagine watching a live interview and it feels like you're right there with the guests. That's the kind of experience EVP is aiming for.
That sounds incredible. It seems like the future of streaming is all about instant access, right? But with all this focus on speed, how do we make sure streams are secure? I mean, we don't want just anyone accessing them.
That's where digital rights management comes in. DRM is all about protecting the people who create the content. After all, they put a ton of work into making these movies, shows, and live events. DRM helps to make sure they get paid for their work and that people aren't just illegally copying or sharing the content.
So it's like a safeguard. Okay, but how does it actually work?
Well, it uses encryption to make sure only people with the right access can watch the stream. The articles mentioned a few big names in DRM like Fairplay, PlayReady, and Widevine.
Those names sound familiar.
They're essentially different ways of scrambling the video stream so that only authorized users can watch it. It's like having a digital lock-and key system for your video content.
So when I subscribe to a streaming service, they give me a key to unlock the content.
You got it. Now, there's also something called Sample A's encryption. It's a bit more specialized.
What does that do?
It's used to encrypt specific parts of a video stream. Let's say there's a scene in a movie that's particularly controversial, or maybe there's some confidential information in a live broadcast. Sample A's allows you to keep those specific parts locked down until it's time for them to be decrypted. It's like a safe within a safe.
A very selective shield. Clever. We've talked a lot about the technology behind streaming, but we can't forget about accessibility. Not everyone experiences video the same way.
Absolutely. Things like captions and subtitles are so important for people who are deaf or hard of hearing, and they can be really helpful for people who are watching content in a language they don't understand.
I've definitely used subtitles when watching movies in other languages, but I've noticed there are different formats like WebVTT, TTML, and SRT. What's the difference between them?
They all essentially do the same thing, display text that's synchronized with the video, but they have some differences in terms of how they're formatted and how much detail they can handle.
Okay, give me the rundown.
WebVTT is a simple format that most web browsers support. Then you have TTML, which is more robust. It can handle fancier stuff like styling and positioning of the text. And then there's SRT, which is super simple and really popular because it works with a lot of different media players.
So it's about picking the right tool for the job.
Exactly. But no matter which format you use, the important thing is that they make video content accessible to everyone.
I think it's awesome that we have these tools to make sure everyone can enjoy video, no matter their abilities or language.
I agree. Now, let's shift gears a bit and talk about the organizations that work behind the scenes in the broadcast world. We've talked about all the building blocks, the protocols, the codecs, but who are the people making sure it all works together smoothly?
That's a good point. We've gone really deep into the tech, but now I'm curious about the people and organizations behind it all. So who are the masterminds behind the curtain, so to speak?
It's really a whole ecosystem with lots of different players. The articles mentioned groups like SMPTE, SET, ETSI, and the ITU. They all play a vital role in setting industry standards and making sure that all the different technologies we've talked about to actually talk to each other and work together. They're kind of the unsung heroes of the broadcast world.
They're like the rule makers, making sure everyone's playing by the same rules.
Exactly. They're constantly working to establish those guidelines and specs that keep the industry running smoothly. But what about the actual monitoring and control of all this technology?
Yeah, is there some giant control room where people are watching everything?
You bet. Picture a room with walls full of screens, each one showing a different video feed.
It's like something out of a movie.
That's where multiviewers come in. They allow operators to see tons of video signals on a single screen. It gives them a complete overview of everything that's happening.
So it's like having supervision, being able to see everything at once.
Precisely. They can quickly spot any issues and make sure everything is running as it should.
Okay, but what happens when something does go wrong? Is there a tech equivalent of a timeout?
You know what? The articles actually talked about a penalty box.
No way, really?
Yep. It's used to isolate problematic feeds. So if something starts acting up, they can quickly isolate it and troubleshoot it without disrupting everything else.
I love that. It's like taking a misbehaving feed out of the game for a bit. But broadcast technology is always evolving. How do they keep up with all the changes?
That's a great question. One of the big things happening right now is a shift toward adaptive monitoring.
Adaptive monitoring.
Yeah, it basically means the system can adjust its monitoring activities based on what's happening in the network at any given time.
So it's like a smart assistant.
Exactly. It can automatically prioritize what needs to be watched most closely so that nothing critical falls through the cracks. It's a really important way to stay on top of things in such a fast-paced environment.
It really is a complex and dynamic world, and we've only just scratched the surface.
We've covered a lot of ground today, from the nuts and bolts of protocols and codecs to the intricacies of streaming and those unsung heroes that keep everything running.
Welcome back to the final deep dive into the world of broadcast tech. We've come a long way from those foundational protocol to all the complexities of streaming, captions, and even the organizations that shake the industry.
It's been quite a journey. And it's amazing how much happens behind the scenes before you hit that play button.
I'm definitely feeling a lot more informed. But before we wrap things up, I wanted to touch on some of those tools and technologies that really power the back end of broadcast operations.
Ah, yes, the stuff that most viewers never even know exists.
Exactly. But without them, the whole system wouldn't run nearly as smoothly. So what have we talked about here?
Well, one that really stood out to me was Elasticsearch. It's basically a super-powered search engine.
A search engine, like Google.
Sort of, but it's specifically designed for the huge amounts of data that broadcasters have to deal with. Think of it as Google, but for broadcast data. They can use it to analyze logs, monitor performance, and troubleshoot problems in real time.
So it's like a detective tool, helping them find those important clues. What else do they use?
Another big one is Redis. It's what we call an in-memory data store.
In memory. What does that mean?
It means it's super fast and efficient because it keeps the data in RAM. It's perfect for things like video delivery, especially for content that gets requested frequently.
So it's like having all the most popular stuff right at their fingertips.
Exactly. And then there's Docker, which has become really important in the broadcast world.
Doctor, I think I've heard of that.
It lets you build and run applications in these things called containers.
Containers.
Think of them as self-contained packages that have everything an application needs to run.
Okay, so it's like shipping the app in a box, ready to go.
Exactly. They're incredibly portable, which makes them super easy to deploy across different systems. This is really valuable in broadcasting where things are always changing so rapidly.
It's all about being adaptable, right? But I'm curious, how do all these different tools and systems communicate with each other?
Well, one of the most crucial protocols is SSH, which stands for Secure Shell.
Secure shell, okay.
It's essentially like creating a secure tunnel between computers so you can access and manage them remotely.
So broadcasters can control things from anywhere in the world.
Exactly, and it's super secure, which is essential when you're dealing with sensitive data.
Speaking of sensitive data, what about those massive video files? Do they still use FTP?
FTP is still around, but these days it's not the most secure way to transfer sensitive data. For something like video files, broadcasters are more likely to use something like SFTP or FTPS.
What are those?
They're basically upgraded versions of FTP that add encryption to protect the data while it's being transferred.
Makes sense. More security is always a good thing. So we've talked about all these different pieces of the puzzle, but how do they all fit together in the big picture of broadcast tech?
One way to think about it is in terms of layers. At the bottom, you have the physical infrastructure, the servers, networks, cables, all that stuff.
The foundation.
Exactly. Then you have the software layer, the operating systems, the applications, databases, everything that manages and processes the data.
Okay, and what's at the top?
The user interface, that's what both the broadcasters and the viewers interact with. All these layers are connected and depend on each other to work.
It's like a giant well-oiled machine with so many parts working together. But how do broadcasters actually measure the quality of all this tech?
There are a bunch of different metrics they use to evaluate how good a video stream is. Things like MOS, SSM, PSNR, VMF. They all use different algorithms to assess the quality, taking things like resolution, frame rate, and compression artifacts into account.
So they're looking at the technical side of things.
Yeah, but it's not just about the technical specs. They also consider the perceptual quality, how the video actually looks and feels to the viewer.
So the ultimate goal is for the viewer to have a great experience.
Exactly. It's a balancing act between achieving technical excellence and making sure the viewer have a smooth, enjoyable, and immersive experience. And speaking of enjoyable experiences, I'd like to take a moment to thank our sponsor for this deep dive, Stonefly.
Yes, a huge thanks to Stonefly for their support.
For our listeners who might not be familiar, Stonefly provides some really innovative storage and backup solutions, and they do some fantastic work with private cloud solutions as well.
So if you're looking for ways to optimize your data storage or streamline your broadcast workflows, Stonefly is definitely worth checking out.
Absolutely. They really understand the needs of broadcasters, and their solutions are built for high performance, scalability, and reliability.
If you want to learn more about what Stonefly can offer, head over to www.stonefly.com or reach out to their sales team at sales@stonefly.com. They'll be happy to help you find the perfect solution for your needs.
And with that, we've reached the end of our deep dive into broadcast tech. We've explored everything from the basic building blocks to the cutting-edge trends that are shaping the future of this industry.
It's been quite a journey. We've decoded protocols, unpacked codecs, navigated the world of streaming, and even met the unsung heroes who keep it all running.
What stands out to you the most? The sheer complexity of it all, the ingenuity of the solutions, or maybe just the fact that something as simple as watching a video involves so much technology working behind the scenes?
For me, it's the realization that technology is always pushing forward. I'm excited to see what the future holds for broadcast tech. Who knows, maybe we'll be back for another deep dive someday to explore those next-generation technologies.
That sounds like a great idea. Until then, keep those questions coming, and remember, next time you watch a video, take a moment to appreciate all that unseen technology making it possible.
And on that note, we've come to the end of this episode of The Deep Dive. Thank you so much for joining us. We'll see you next time for another fascinating exploration.